Welcome back. In today's lecture, I will be discussing a very important topic, that is a dipole and an electric field due to a dipole on its axial line, its equatorial line, it's also called neutral line, and then we'll generalize the case that how to find out electric field due to dipole at any arbitrary point. So this is very important case. This will be followed by the expression for potential energy and torque on a dipole when it is placed in external uniform electric field. So this will lead to the stable and unstable equilibrium, the understanding of stable and unstable equilibrium. This is a really important topic. I hope you will concentrate on it. So first of all, what is a dipole? Dipole, as the name is suggesting, it has got two poles. That means two charges of opposite polarity separated by a fixed distance. That is what we call a dipole. You are definitely familiar with this term. You must have studied about dipoles in chemistry. For example, you have got a molecule like HCl. We know that from chemistry study that chlorine is a bit more electronegative than hydrogen. So what happens? The shared pair of electron is drawn towards chlorine, chloride ion, and it becomes delta negative and hydrogen becomes delta positive. So this is a simplest form of a dipole. Two equal and opposite charges separated by a fixed distance. In this case, the fixed distance is the bond length. So you are familiar with this dipole, and we'll study in this lecture the physical aspect of it, how its electric field varies with distance in different directions. So let's see what is a dipole. So dipole is a combination of two equal and opposite charges separated by a fixed distance. For simplicity, for mathematical convenience, we generally take that distance to be 2L, so that from the center, one charge is L distance in one direction, the other charge is again L distance away in the other direction. The standard dipole is given by a parameter called dipole moment, which is generally denoted by small p, and it's a vector quantity and its direction is from negative charge to positive charge. Its direction would be from negative charge to positive charge. This is just the opposite. If you have studied this dipole moment concept in chemistry, chemistry people would say that dipole moment is from positive to negative, but in physics we take the direction to be opposite, from negative to positive. Doesn't make any difference. The direction is purely conventional in nature, and whichever convention the chemistry people are following or whichever convention the physics people are following, there is no problem at all as long as we stick to a particular convention. So in physics we follow this convention that the dipole moment is from negative to positive direction. And the magnitude of dipole moment is given as the product of either charge. Both of them are equal, so either charge q without sign, q into the distance between the charges. In this case, the distance between the charges are taken to be 2L, so dipole moment turns out to be q into 2L. Now let us find out the electric field due to dipole on its axial line first. Let me redraw. Although we are considering these charges to be point charge, just for pictorial clarity, I am making them big. Don't get confused with that. The charges which we are considering in ideal case are point charges. I am drawing them big for pictorial quality. That's all. So this line, extending either way. This is what we call as the axial line. This is the axial line. From center, let's say I consider a point P from center at a distance x, where I wish to find out electric field due to this dipole. See, I apply the principle of superposition which we did earlier, that instead of we simply cannot find out electric field due to both the charges together. So what we'll do, we'll find out electric field due to positive charge, electric field due to negative charge, and then we'll do the vector sum of these two. How can we do that? Wherever you wish to find out electric field, just put a small test charge plus Q naught from your own side. Now, the plus charge will repel this positive test charge away from it. So, the electric field of this positive charge is in this direction, E plus. I call that E plus, it is in this direction. Whereas the negative charge is going to attract this test charge towards itself. So this is, let's say, the electric field of negative charge. I call that E negative. I know that these two vectors are acting along the same straight line. So resultant vector would be simple subtraction of the two. So the effective electric field can be written as, effective electric field would be E plus minus E minus. Now, I know that the positive charge is closer to point P. That means the effect of plus Q would be larger than the effect of minus Q. Therefore, the electric field E plus would be bigger in magnitude than E negative. Therefore, I am taking it as E plus minus E minus. And I have foregone the sign of these quantities being vector, the small arrows on the top, simply because I know that they are acting along the same straight line and resultant can be obtained by simple subtraction. I wish to find out the magnitude. I'll tell you about the direction later on. Now, how to find out E plus? I know that this distance is L and this distance is X. So, what is the distance of this positive charge from point P? This is X minus L. And in a similar way, what is the distance of this negative charge from point P? This is again L. So it was X up to this point and L it is further away. So it becomes L plus X from point P. So total electric field E can be written as 1 by 4 pi epsilon naught Q, that is the due to positive charge, Q divided by distance from the positive charge is X minus L whole square minus 1 by 4 pi epsilon naught. Charge is again Q. Just take the magnitude, don't take the sign. We have adjusted the sign by considering the direction. Q divided by X plus L whole square. What do I get? Whatever is common, I take it out. Q by 4 pi epsilon naught. And inside the bracket, I have got X minus L whole square minus 1 by X plus L whole square. I can further simplify it. Simple algebra. Total electric field at point P, this is lying on the axial line, is given as Q by 4 pi epsilon naught X plus L whole square minus X minus L whole square divided by X square minus L square whole square. I know A plus B whole square minus A minus B whole square would be 4AB. So it turns out to be Q into 4AB, that means 4 times X into L divided by 4 pi epsilon naught X square minus L square whole square. I know Q into 2L is P, so what remains is 2px over 4 pi epsilon naught X square minus L square whole square. The electric field at a point P lying at a distance x from the center of the dipole is given by this expression, that is 2px over 4 pi epsilon naught X square minus L square whole square. What is the direction? Since this E plus vector is bigger than E minus vector, therefore the overall subtraction will have the direction of E plus. That means electric field at a point on the axial line is acting in this direction. This means that on axial line, the direction of electric field E is same as that the direction of dipole moment P. This is important. Electric field at a point on axial line of a dipole has the same direction as the direction of dipole moment. Now, I can do a small special case as well. What if this point P lies very far away? What if this point P lies quite far away, then I can simply ignore L in comparison to x. What would be the expression for electric field at a point on the axial line which is quite far away from the center of the dipole in comparison to length of the dipole? It would be E. I am assuming that x is very greater than L, so I ignore L in this expression. What do I get? X square whole square, that means x raised to the power 4. I've got 1x in the numerator, so what do we get? E is equal to 1 by 4 pi epsilon naught 2p by x cube. You should keep both these expressions committed to your memory. They will be really handy to be used later in the numericals. So this is the expression for electric field due to a dipole at a point on its axial line, and the direction of electric field on the axial line is same as that of dipole moment. What if I take the point on this side of the dipole? Let's say the point P was lying on in that direction. What would be the direction of electric field in that case? It would still be same as along the dipole moment. Check it out yourself. I'll go to the next topic. Now, in next topic, I would find out electric field due to a dipole on its equatorial axis. This line, perpendicular to the length of the dipole. That's called its equatorial line. It is also called neutral axis of the dipole. Why it is called neutral axis, that you will realize when we'll do the topic of potential. I'll tell you later on, just take it for granted for the moment that potential at every point on this line is 0. Therefore, this line is called neutral axis. Electric potential will be 0. But that will prove later on. At the moment, we are interested in finding out electric field at a point on the equatorial axis. Let's try and find it out. Again, a same dipole. I've got minus q charge over here, plus q charge over here. The total length is 2L as usual. The length from the center, the distance of each charge from the center of the dipole is L. This line is equatorial axis. So what do I do? Let's say this is the point P where I wish to find out electric field. It is at a distance x from the center of the dipole. What do? I place a small positive test charge over here and see what happens. Now this positive charge will push it away from it because both of them are positive. The like charges repel each other. This electric field at point P due to this positive charge is acting along this line. Let's say I call that E plus vector, whereas the negative charge is going to attract it in this direction. Let's say electric field due to the negative charge, I call it as E negative vector. Now the resultant electric field of E plus and E minus would be the net expression which we are looking for. For that, what do? We complete the parallelogram and resultant acts in this direction. This is the resultant we are interested in. So how to proceed with this? Let's find out first of all E plus. If this distance is x, this distance is L, this is hypotenuse of this right angle triangle. You need not to tell you that it is under the root x square plus L square. So distance of this point P from the charge Q plus is under the root x square plus L square. So what would be E plus magnitude? It will be equal to 1 by 4 pi epsilon naught charge divided by distance x square plus L square under root whole square. Square and under root get cancelled out. What do I get? Is 1 by 4 pi epsilon naught q divided by x square plus L square. Now this is the expression for E plus. This is the expression for E plus. What is the expression for E minus? Interesting. Again, the charge is same and distance is same under the root x square plus L square. So electric field is again same. 1 by 4 pi epsilon naught cubed by x square plus l square whole square, or sorry, square get cancelled out with under root. Now we need to find out, we have already obtained that E plus is equal in magnitude to E minus. They have got different direction but magnitudes are same. So let's see how to find out the result. If this angle is theta, need not to tell you that this angle will also be theta. If this angle is theta, this is also theta. I can resolve E plus into two components. This will be E plus sine theta, and in this direction I will have E plus cos theta. Similarly, on resolving E negative into its rectangular components, I will have E negative sine theta, and in this direction again E negative cos theta. So what we see, since E plus and E minus are equal in magnitude, these sign components get cancelled out, and only resultant electric field is equal to sum of these two. That is, the resultant electric field is equal to E plus cos theta plus E minus cos theta. Since E plus and E minus are equal, I can write it down as 2E plus cos theta. Put in the value of E plus from here and the value of cos theta from this triangle. What do I get? E is equal to 2 times 1 by 4 pi epsilon naught q divided by x square plus l square into cos theta, which is base over hypotenuse. This is L over under the root x square plus l square. Q into 2L is nothing but P. What do we get? E is equal to 1 by 4 pi epsilon naught P divided by x square plus l square raised to the power 3 by 2. This is the expression we are looking for. Q into 2L was P, 4 pi epsilon naught as such, x square plus l square raised to the power 1, and under root means power 1 by 2, base is same, so the powers get added up. So what do we get? E is equal to 1 by 4 pi epsilon naught P divided by x square plus l square raised to the power 3 by 2. Now what is the direction? Direction of electric field. You can pause the video here, think for a moment, and when you are ready you can come back. Look at the diagram. The electric field at point P, which is lying on the equatorial axis, is opposite to dipole moment. The dipole moment is from minus charge towards plus charge. That means dipole moment is acting in this direction, whereas the electric field is at 180 degrees, at an angle of 180 degrees, or simply you can say opposite to the direction of dipole moment. So magnitude is 1 over 4 pi epsilon naught P by under the root, not under the root, P by x square plus L square raised to the power 3 by 2, and direction is opposite to the dipole moment. We can do the same special case as we did earlier for this expression as well. If x is very greater than L, that means the point of observation lies quite far away from the center of the charge, the center of the dipole. You can simply neglect L in this expression, and what do we get? 1 by 4 pi epsilon naught P by x cube. Did you notice? Did you notice that electric field at a far off point for an axial line, electric field at a far off point on axial line was twice this much. That means for x very greater than L, E equatorial is equal to 2 times E axial is equal to 2 times E equatorial. Further, I may ask you, what is the angle between electric field at a point on the axial line due to dipole and the electric field due to that same dipole on its equatorial line? Since they are opposite, on axial line the electric field was along the dipole moment, on equatorial line the electric field is opposite to dipole moment. So this makes a beautiful question, that what is the angle between electric field due to a dipole on its axial line and the electric field due to the same dipole on its equatorial line? The answer is 180 degrees. They are opposite. And further, there is one more point to consider. You see, for point charge, when we were considering electric field due to a point charge, let me clear it a bit. When we were considering electric field due to a point charge, the expression for electric field was 1 over 4 pi epsilon naught q by x square. Whereas, if we are dealing with a dipole, electric field is 1 by 4 pi epsilon naught p or 2p, whatever, divided by x cube. That means E is proportional to 1 by x cube. In this case, E was proportional to 1 by x square. That means the electric field due to a dipole falls off more rapidly than electric field due to a point charge. I repeat, electric field due to a dipole falls off more rapidly than electric field due to a dipole. That means if you increase the distance, or if you make the distance twice for a point charge, electric field will become 1/4 of its previous value. Whereas in this case, if you double the distance from the center of the dipole, electric field will become 1 by 8 times its previous value. This is about electric field and its direction due to a dipole on its axial line and on its equatorial line. In continuity to this lecture, in part 10, I will generalize this expression, that electric field due to a dipole at an arbitrary point, and then two more small, very important articles. The electric field due to the torque on a dipole placed in external electric field, and potential energy of a dipole placed in external electric field. So, and these two lectures will complete the theory part of the study on dipole. We'll come to that later on. Thank you.